So my name is Kudlis Andrey, and first of all, I'd like to thank Ivan Shulik for the opportunity not to cover all the results which I've obtained in the close collaboration with other my colleagues, and also thank Ivan Yosh for the opportunity to tell about something new within this session. Yes, and first part, as from our previous colleagues, will be devoted to some scientific problem, which I found the most probably interesting, the most peculiar, and the problem which can be more or less absorbed by our colleagues, understanding of the problem within these 15 minutes. Motivation. Okay, we've decided to choose some material system, some toy model, and placed it to the optical microcavity. And we've analyzed the changes of properties, in particular, how energy transfer should be modified in the presence of resonator mode. So, motivation. It's not a secret. There is a rapidly growing direction of research called chemical polyretonic chemistry, chemical polyretonics, where people try to analyze the changes in behavior when they put some material system to the optical microcavity. And the prime of importance here, it is the regime of strong coupling interaction between light and matter. In particular, due to the special coherence of polyretons, which appear in this case, we can observe the substantial modification of energy transfer. And moreover, in the so-called of deep strong, ultra strong coupling regime, the system demonstrates substantial modification of ground state. So, within this analysis, within this area, the most common direction, it is analysis of two limiting cases. First of them is just a small number of, let us consider the most trivial system, just two-level system. And in particular, a little bit more than 10 years ago, the exact solution was obtained for the Andrey model. And the second limiting case is just a so-called thermodynamic limit, where we should consider asymptotically a large number of these material subsystems. But what about intermediate case? What about intermediate case? And here we should first start to think about methods which we should apply to analyze such kind of models. First, we can look at some DFT techniques, and we did it initially because before we've prepared this work, we tried to extend QED DFT approaches and suggest some asymptotically correct energy functional. Asymptotically, I mean in terms of the number of material subsystems. And of course, as benchmark, we've used exact diagonalization. And we've noticed that the observed phenomena, which I will show you, cannot be catched, cannot be explained by the most commonly used random phase approximation. And within this analysis, we've decided to limit ourselves by just exact diagonalization, because we are talking about mesoscopic systems. What we have done, we've taken many dimers and distinguished them on two groups. One of the group to one of the group we applied static external potential, and to another group we did not do it. Okay, and we start just to vary this external potential applied to the, in our case, to the second group of dimers. All of them are identical to each other, but they do not interact with each other without any overlapping. And the Hamiltonian of the system is as follows. First term corresponds to the hopping. The second term, it is just interaction with external static potential, kinetic energy of harmonic oscillator, and interaction matter and our cavity mode. So this model can be recognized as some kind of generalization of Dickey model, and it is well known already that for generalized Dickey model, the long-range interaction between two-level systems is realized via cavity mode, and we've observed it. And we've decided to analyze the following quantities. It is just a polarization of one specific. Okay, we can formally write here some averaging, but due to the fact that they all within one group, they all identical, we can just analyze sigma z of any specific dimer, and the total polarization, just average value of this of SZ operator. What we've obtained in supplemental materials, you can find for similar pictures for different combinations of dimers. It's enough interesting, and we've analyzed this kind of behavior. Okay, on the right, it's quite complicated picture, but I try to clarify it. On the right vertical axis, within each picture, we see the values of total polarization. And but on the picture, the behavior of total polarization is marked by blue dashed line. We see abrupt, almost we can conclude, quantized behavior of total polarization depending on the value of external potential applied to the second group. Also, we see that for the first group of dimers, we see a non-monotonic behavior of some averaging of sigma z, or just a polarization, which is here labeled by D1. And due to the dominant character of the interaction term, I mean the lambda square, yes, it's important comment. No, not how many minutes do I have?
5 more minutes for everything.
Okay.
Okay, no problem.
I should do it. Okay, we should mark that this kind of behavior can be observed only when this system parameters satisfy the following condition. And we've decided to plot some kind of diagram where on the axis we've written the values of some dimensionless combination of system parameters, and we see some region where this quantized behavior of total polarization is observed. So, in order to give some qualitative explanation, we've decided to apply Bohr-Oppenheimer cavity approximation and forget about kinetic energy of harmonic oscillator and replace Q operator just by C number. And by means of this simplified Hamiltonian, we've plotted Born-Oppenheimer energy surfaces, and true ground state can be obtained just by finding the minimum value in terms of Q variable. And if you look at the pictures on the upper panels, you see, for example, dotted lines were constructed by means of this Hamiltonian. And dashed lines, red and green ones, also were obtained by means of this Hamiltonian. And we see that the main features of behavior were captured. So, but we've decided to go further in order to analyze the structure of this local minima, which are the core of the observed effect. And we've also decided to perturbatively handle the term which correspond to Hoping. Initially we decided just to forget about it, and in this case we deal with the eigenstates of just sigma z operators. Yes, and energy can be exactly obtained, and it's not. It's easy, of course. We can construct some figures, and for t is equal to 0 and external potential equal to 0, we have n plus 1, where n is just a total number of diameters. We have n plus 1 local minima. When we turn on external potential, this degeneracy is reduced to the n1 plus 1. And next step, we also can turn on hopping and perturbatively take into account the hopping. Yes, this TSX contribution to the Hamiltonian. Based on the structure, based on the perturbation, the structure of perturbation theory, and eigenstates of unperturbated model, we understand that first corrections can be obtained only within the second order perturbation theory. And this contribution lower ground state. And if we look again, for example, and at this case, maybe it's not so obvious, but inclusion of this, for example, only the second order perturbation theory term, we see that this minimum is more affected than this one, because it is just closer to this and to this. So to sum up, we also decided to plot some maybe advanced case with many number of dimers, and we've found some phenological formula for the number of steps which you can observe on this picture. Here we've also presented some thoughts, some ansatz regarding how to explain the steep, how explain the how long the step. It can be just done if we associate each minimum with some coherent state of harmonic oscillator and consider the whole wave function as just a linear combination, and try to analyze some probability of tunneling between these local minima. So some remarks. This behavior, yes, is on can be observed. Sorry for the typos. Can be observed only in the mesoscopic system. Yes, and this also effect vanishes when we take thermodynamic limit and it's not probably difficult to understand because, for example, for red line, it just goes to the one huge step, and these small steps will be smaller and smaller, and at some number of dimers, it will be difficult to just to distinguish, to identify this step itself. So some notes probably which are important for our further analysis connected with further advancing of QED DFT approaches. Probably I should skip it. And to conclude, I'd like to say that we've demonstrated non-perturbative behavior of the system, which consists of some finite number of material subsystems. In our case, it's just dimers, and quantized dependence of total polarization of static external potential. And we've also presented some qualitative explanation of the effect, which was supported by exact diagonalization analysis. So at the end, I'd like to draw some achievements from the moment of my employment within ACTP. It was in January this year, which you see three first points is connected with my proposal, and regarding the second point, as Professor Shelikh told us, we've obtained two positive reports from the referee in physical review B. Regarding the third point, all work and almost all the parts of the publication is prepared. I think it is just a question of 1 month, because all of us, all of our courses, a little bit busy now. And regarding the first point, which is connected with scientific part of my talk, we are waiting for the second answer of the referee from the physical review letters. Yes, and fourth, fifth, and sixth points are connected with my other scientific activity, and it was necessary to perform it because I should finish my report for grant within the Russian Scientific Foundation. And of course, it is connected with critical phenomena, with critical behavior theory. And as Professor Altshuler asked me, stop to do some epsilon expansion stuff. Okay, I did it, but I should also finish this stuff. Okay, about grant, I've applied for one new grant. About my plans, some short period plans. One of them is connected with the analysis of some revision of trionic behavior in magnetic field for some non-conventional potentials, and another one which is connected with the role of the big excitons in the TMD monolith. Thank you very much for your attention.
Thank you. Please, questions?
This deep strong, there is already ultra strong, hyper strong. So have you invented this term yourself?
It is the most probably tricky question. You won't obtain from me numbers or what?
Just place it, yeah, because we know that ultra strong is a bit weaker than hyper strong. Yes, and there is strong and there is probably.
Okay, in our paper we've written ultra strong.
Yeah.
We didn't invent any new
Classification.
So there are pretty a lot of names, so we didn't use any new. So like what they say usually is that ultrasound is so you have dimensionless parameter, light matter coupling strength divided by the frequency. So ultra strong starts when this parameter becomes larger than 1/10, 1/10.
Right.
But then if it can become larger than 1,
It is hyper strong.
well, I didn't hear hyperstrong yet.
I think it's deep strong.
Yeah,
Deep
this is
strong.
deep strong.
Oh, it's deep strong.
Yeah.
Yeah.
This is deep strong.
We are in a deep strong.
It is hyper strong.
Okay. Other questions?
Is it somewhat similar to column blockade effect? Because it looks very similar.
Okay, I just don't know.
You have something quantized in steps. Yeah.
We are now trying to
I'm
squeeze it into something similar.
Boris, please.
I just want to ask about the extended decay model. It was very quick, so I couldn't tell, but decay model is integrable. And some of its extensions also are integrable and in a sense can be reduced to all these Gaden type of models. Your extension violates integrability or not? And can you kind of make use of the at least the model being close to the integrable?
It's still integrable, but one second. Okay. Okay, your question about violation of integrability of this model.
So
No,
is
no,
is it violated or it's still integrable?
Okay, be honest, I did not ask myself, but okay, some intuition, let's say no. But maybe I'm mistaken. Sorry, I cannot answer because
Okay.
I don't know.
Maybe later. Because it might be interesting because integrability tells you a lot of many things, including dynamics, which might be next step of studying this.
I'm not planning to leave this model, yes, because probably we will take into account we want to analyze some dynamics. And yes, thank you for the question. I will be ready to answer next time for sure.
What we know is that the Rabi model, which has only one two-level systems, but like arbitrary strong interaction, it is integrable in the sense of Young-Baxter only at certain values of parameter, and generally it's not integrable. Whether this holds for our generalized decay or not, we actually didn't check, but thank you for the question. We'll have to check that.
Okay, but there is also some peculiarity connected with solvable, but not integrable.
Well,
And
yeah,
so, okay,
Wait.
okay, so stop. Thank you.
Okay. Other questions?